This screencast is going to focus on the first 4 sections of Chapter 14, which gets us into equilibrium chemistry based on acids and bases. So the first 4 sections are actually review from first-year chemistry, which is why we're treating this as a review, and you're completing the notes outside of class. So we learned about 3 theories for acids and bases in first-year chemistry. College Board has taken Lewis acid-base theory out of the curriculum, so we won't discuss it here. But Arrhenius and Bronsted-Lowry are still fair game. So if you remember in the Arrhenius concept, acids were anything that increased the concentration of H+ in solution. And bases were anything that increased the concentration of OH- in solution. So something like NaOH would be classified as a base because when you put it into water, it dissociates and breaks up into Na+ and OH-. So that would increase the concentration of OH-. For the example of an acid, HCl would break up into H+ and Cl-. So it would be an acid in the Arrhenius sense because it increases the H+ concentration. So then we look at Bronsted-Lowry theory, and that's the one we tended to spend more time on. And it looked at what was happening with protons. So acids were proton donors, so they were anything that donated protons. And bases were proton acceptors. And those occurred in concert with one another, meaning that if you had an acid that wanted to give up a proton, then you needed to have a base that would be there to accept that proton. And that's where we came up with acid conjugate base pairs. So when we look at like a general acid, the way they've given you this dissociation equation down here, HA can just stand for any type of acid. We see the double arrow there, which leads you to believe that this is probably a weak acid. And what you do is you try to find the things that look most alike. And you always want to look at these reactions from left to right. So if I pair up HA with A-, what did HA have to do to form A-? Well, it had to give up a proton. So that means HA is our acid, and his partner is called the conjugate base. And we'll talk about why he's opposite in a moment. And then water, to go from H2O to H3O+, he had to accept a proton. So that means he's a Bronsted-Lowry base, and his partner is a conjugate acid. So students look at that sometimes and they're like, well, why are they opposites? And it has to do with this arrow. If we look at a reaction simply from left to right, acids can donate their protons and form other products. Well, if this is a reversible reaction, meaning if the products can form back the reactants, if we were going to go from A- back to HA, what would A- have to do? And the answer is A- would have to pick up a proton, and picking up a proton is acting as a proton acceptor, and that's like a base. So that's why these are conjugates. So conjugates will always be on the product side. Don't ever put conjugates on the left. And you always want to match up and just kind of find the partners. Sometimes what we'll write is kind of the simple equation, which is just HA breaking up into H+ and A-. This is kind of the lazy way to write it. We write it that way a lot. But the difference between is, are you showing the water or are you not showing the water? So if water accepts a proton, it's called a protonated water, and it forms hydronium ion, right? So if we leave that water out and we just show the HA breaking up into A- and H+, it's understood that this is H3O+. Okay? So either is really acceptable, and you see in the Ka expression, it's still products over reactants. So in practice 1, we're just practicing writing out the general and the simple dissociation. So if my acid now is HCl and I put it into water, we're going to do a single arrow because HCl is a strong acid. So it'll break up into H3O+ and Cl-. So the simple would just be saying HCl yields H+ and Cl-. So if I want to identify my conjugate acid-base pairs, to go from HCl to Cl-, he had to lose a proton. So this is our acid, this is our conjugate base. To go from water to H3O+, he had to gain, so he's our base, and that's our conjugate acid. Write the equilibrium expression, so KEQ equals. Now we can write this out, but again, we've got a single arrow, so this is not an equilibrium condition. but we can certainly write it out, H3O plus times Cl minus all over the concentration of HCl times the concentration of H2O. This forward reaction completely happens, which tells you that these basically go to 0, and we wouldn't have an equilibrium. But just for practice, we can do that. Then we've got NH4 plus being placed in water. This will be an equilibrium condition. So he's going to give up that H, and all will be left is NH3, and then water becomes H3O plus. So again, find your partners. So to go from NH4 plus to NH3, he had to give up protons. That's our acid. NH3 is our conjugate base. Water here is accepting the proton, so it's acting as our base, and this guy is our conjugate acid. If we wanted to write it kind of in the simple terms, NH4 plus breaks up into H plus and NH3. And then our equilibrium expression, we would say K equals, on top, we would have NH3 times the concentration of H3O plus, all over the concentration of NH4 plus, times the concentration of H2O. Alright, when we talk about acid strength, there's different types of acids, and we've certainly covered this. Strong acids versus weak acids. Strong acids 100% dissociate. They're going to have huge K values. They're usually not even listed in the table. Versus weak acids are going to have small Ka values because not much product is formed. So it's staying mostly on the reactant side and not much is breaking up. These form strong electrolytes, these form weak electrolytes. Just some vocabulary that you're comfortable with. Monoprotic acid means there's just the one proton. Diprotic means two. Sometimes they'll call diprotics polyprotics, which just means they have more than one, and then that, is less specific than saying a diprotic or a triprotic. Oxyacids are anytime you have those polyatomic ions that have oxygen in them, they call them oxyacids. And then organic acids, we learned right before Christmas break about the COOH functional group, and of course this is the H that pops off to make that an acid. So the neat thing about water that we talked about in first year was that it can act as an acid or a base, and we actually saw that just a few minutes ago with the NH4 plus and the HCl. Water can take on a hydrogen and form H3O plus, or it can lose a hydrogen and form OH minus. So substances that can do that are called amphoteric substances, or it exhibits amphoterism, and that just means it can gain a proton or it can lose a proton. Now, you saw Kw in first year chemistry, but it certainly didn't mean a whole lot because we didn't do any equilibrium. But this is just saying that when water breaks up, it's constantly doing this. Water reacts with the water and makes hydronium and hydroxide. There's actually an equilibrium that's established. So even though we think about just H2O being in a beaker, it's actually a mixture of these ions. And so this sets up an equilibrium condition called Kw. In Kw, when you take the products, right, these, assuming that these are both pure liquids, it would just be the H3O plus concentration times the OH minus concentration equals this constant value. And this is where the pH scale comes from. You'll see 14, and that's not a coincidence. So if you're looking at a balance, if H plus is greater than OH minus, then we know it's going to be acidic and the pH will be less than 7. If the H plus is less than OH, meaning the OH is winning, then it'll be basic and the pH will be greater than 7. And if these two are equal, it's a very special condition, that means you are neutral and your pH is equal to 7. So we're going to work out some examples with just calculating using Kw. And of course, we've learned kind of a workaround so that we didn't have to use the Kw in first year chemistry, and you're certainly welcome to work it out that way as well. Alright, so this gives you the OH minus concentration. So we know that Kw is a constant, 1.0 times 10 to the negative 14th, and that's just equal to the concentration of H plus times the concentration of OH minus. So if I know OH minus, he's going to go in there, I come and I calculate. That gives me an H plus concentration of 1.0 times 10 to the negative 9. That's one you can actually do without a calculator because the bases are 1. And so what that means is H plus is smaller than OH minus. So this would be a basic solution. And then H plus is given in this one, so we would say Kw equals H plus plus times OH minus. We know 1.0 times 10 to the negative 14th equals 1.0 times 10 to the negative 3rd times the concentration of OH minus. So solving for OH minus, we get 1.0 times 10 to the negative 11th. So very, very, very small hydroxide ion concentration, which means the H plus is winning, and this would be an example of an acidic solution. So the pH scale runs, you know, typically we talk about it running from 0 to 14. You can certainly have numbers greater than 14. You can have numbers that are negative, which just is saying that it's really acidic. So it's a log scale. These concentrations that we just saw, right, on the order of 10 to the negative numbers. And so if we log that, then it makes it nicer numbers to deal with. So less than 7 is acidic, greater than 7 is basic, and you can talk about anything around 7 being near neutral. So these are all the calculations, the formulas that you saw in first year chemistry. And I don't believe we did the new sig fig rule. It's been a while since you've learned the new sig fig rule. So here it is, and it's about natural logs in particular. So it says that the number of decimal places in the log is equal to the number of significant figures in the original number. And so I'll show you how that works. But for example, if we were going to look at 6.88, that number has, somebody's taken a log of a number to get there. So you look at the number of decimal places. So it has 2 decimal places. So you're going to give its concentration, which, oops, went past it there, is H plus. This would have 2 significant figures. So here, if you have 2 significant figures, when I go and I take the log of that, that actually tells me how many decimal places I have. So when I work backwards, right, the POH would still have 2 decimal places. So sometimes sig figs will differ between a pH and a POH, and that's because you're matching decimal places, you're not matching sig figs. All right, so let me do solution A for you, and then if we need to do more practice, we certainly can, but it will probably come back to you as we go through it. All right, so we know that there's a special relationship, pH plus POH sums up to 14. So if I know that the pH is equal to 6.88, to get my POH, I just have to subtract. So I would do 14 minus 6.88, and I would get 7.12. Whenever you classify, you always want to classify based on the pH scale, because that's what you guys are comfortable with. You've seen that since like middle school, maybe even late elementary school. And so less than 7 to you says acidic, or you could even say near neutral, because it's pretty close to 7. All right, so to get my H plus, I'm going to do 10 to the minus pH. So I would do 10 to the minus 6.88. All right, that has 2 decimal places, so the concentration is going to have 2 sig figs. So that comes out to 1.3 times 10 to the negative 7th molar. To get my OH minus, I'm going to do 10 to the minus POH. Or I could use that formula I was just using before, the 1.0 times 10 to the negative 14th. You get very similar answers. So we would do 10 to the negative 7.12. Put that into your calculator. It's going to have 2 sig figs, 7.6 times 10 to the negative 8. And so you can work backwards between all these different formulas. All right, so here's our list of strong acids. And the special thing about strong acids is that they fully dissociate. Some lists will also include HClO3, okay? So you can kind of put that on your radar as well. It just means that these guys are not equilibrium systems, that they get 1 arrow. And the nice thing is that the concentration is just equal to the H plus concentration. So again, we did ones like this last year where we said, or the year before, whenever you took chemistry. If I know this concentration, it's kind of similar to an ionic salt breaking up. So it fully does this. So it forms 0.1 of H plus and 0.1 of Cl minus. We don't really care so much about the Cl minus because to get the pH, we're going to negative log the H plus, and so we're going to negative log the 0.10, and so we get a pH of 1.00. So again, all right, you do want to watch out for any acid or base that they list, and you look at that concentration and you think, ooh, that's really, really tiny. Usually if it's less than smaller number than 10 to the negative 7, so 10 to the negative 8, 10 to the negative 9th, this is considered exceptionally dilute, and the autoionization of water takes over, and so the pH would just be equal to 7.